Welcome to the Henstitute. For this one, we are going to be talking about the force on a current in a magnetic field. So as we have some kind of current flowing through here, so the idea of this picture over here is we have a battery that's been connected up here, and it's causing current to flow from the positive down through this wire, and then come across here and then travel back up. So they have a picture of that to show the direction of it. And we know that there should be a magnetic force when you have a charge that is moving in a magnetic field. So it's equal to the cross product of that. Remember, we think of currents as actually the movement of positive charge. So I is the movement of positive charge, thanks to good old Ben Franklin. Then we can actually modify this a little bit. So if we take our charge and divide by the time interval that it's moving for, and then we take our velocity and we multiply it by the time that it's moving for, then what we end up with is we end up with a brand new equation. And this equation says that the magnetic force is equal to, so Q over T is the amount of current that's flowing through something, and V times T is actually the distance it's traveling through. So it would actually be the length of the wire, and then we still have our B over here. So usually what we do is we think of kind of the charge or the current as actually having a direction, and then our magnetic field being over here. So I usually think of I as being direction and then crossed with B. And so in this particular case, if I use the right-hand rule, my finger, my index finger is going to point in the direction of the current here. So my index finger would point in that direction, and then my middle finger is going to actually point in the direction of the magnetic field. So the magnetic field is pointed downward, like so. So my current is going this way, and then the rest of my knuckles are going to come around like this, and my thumb would actually indicate the direction of the force on this. So my thumb would actually be pointed out in this direction. This is an absolutely horrible picture of my situation here, but the idea is my thumb is actually pointed out here. I'm going to erase this finger for a moment. Let's see if I can fix this and make this a little bit better. So instead, my index finger is going to point My index finger is going to point in the direction of the current, and then my middle finger should actually be heading this direction. So my middle finger is going to point down like so, and then here would be the rest of my hand. So this would be the direction of my thumb. So my current is going this way. The magnetic field is pointed down, and the force on it would actually be in this direction. So that's why if you see this little dotted line here, they're indicating that this current gets pushed upward. So the force acting on it would be in this direction, and therefore it would cause this little wire to actually bend upward. But actually the only part that's going to feel that force is the one that's actually moving diagonally across. This part is the only one, because this part of the wire and this part of the wire are actually moving in the same direction. So when I think about this and I think about my force is equal to I times L times B, and it's going to be the sine of the angle between them, where theta would be the angle between I direction and B direction. If they're moving in the same direction, if theta is actually equal to 0 degrees, and we know that the sine of 0 degrees is 0, and therefore we would have no force. So the only part that's actually feeling the force is the bottom section that's coming across. So not the best picture of a hand, but the best I can kind of come up with. And this is going to give us a new way of looking at the magnetic force, but now we're looking at a current flowing through a wire, since basically a current flowing through a wire is moving charges. This has been another edition of the Henstitute, and we'll try out some problems that kind of relate to this.